All right, well, let's try another example. Let's do an application of this. All right. We've been talking about the idea that we have rates of growth or decay, a rate which is proportional to itself. And as a matter of fact, when we talk about half-life, this is exactly that sort of quantity. Certain radioactive isotopes have a half-life, and we say that the rate of decay of these particular isotopes are proportional to themselves and have a certain half-life. Well, that means that they actually follow this model. As we've been talking about, the model is y is equal to some constant times e to the kt. Right? Since we already know this is our end product, let's go ahead and use this model to talk about radium-226. And let's say we're told that radium-226 has a half-life of 1,599 years. So after 1,000 years, there's 1.5 grams left. What was the initial quantity? And how much will be left after 10,000 years? Okay, we need a little bit of work to find this one, but it's not awful. So let's see what we can do. Well, first of all, if we have a half-life of 1,599 years, that actually tells us that, well, whatever our initial quantity was, we know that our initial quantity means that at t equals 0, y will equal c grams, right? However much we started out with. So if we have a half-life, that means that at t equals 1,599 years, we know that that means, well, c, that y will equal 1/2 of whatever c is. And that's kind of useful because, well, now that gives us an opportunity to solve for our constant, right? Our constant k. Well, I'll show you how, because if 1/2 times c is equal to c times e to the k times 1,599, right? We notice that the capital C, right, that constant is going to just drop out so that we're left with 1/2 equals e to the 1,599 times k. All right, so how does that help us? Well, let's take the natural log on both sides. The natural log of 1/2 is going to equal 1,599k. And so, of course, that means that our constant k is going to look something like the negative of the natural log of 2, see my previous discussion, divided by 1,599. Now, in fact, we can work out the decimal for that if we want to. I'm going to leave it in this form for the moment. All right, so what does that mean that I'm going to get? Well, now I know that my model fits this description. Y is equal to some constant times e to the, this constant k, negative natural log of 2 over 1,599 times t. Right? Okay, so what else do we know? Well, after 1,000 years, 1.5 grams is left. Well, now we're just going to go ahead and solve, right? 1.5 is the amount that we have after 1,000 years. So e to the negative natural log of 2 over 1,599 times 1,000 this time. So doing a little bit of decimal work right here in my calculator. What did I work out? Well, that works out right here. If we take e to this constant and then divide on both sides, I found that c was equal to 2.3139. And you notice I'm carrying it out to at least 4 digits. And that's useful to me because now I've got a model that I can use. Y will be equal to 2.3139 By the way, this is the number of grams that I have initialed. Right, so this is my initial amount. Okay. So y is equal to 2.3139 times e to the negative natural log of 2 over 1,599t. Right, and the question was asked, well, what will be left after 10,000 years? All right, well, let's work that out. Y will equal 2.3139 times e to the negative natural log of 2 over 1,599 times 10,000. 1, 2, 3, 4 big old zeros right there. What do we come up with? Well, I come up with 0.0303 grams at 10,000 years. Well, that's what we were looking for, so we're done.